Okay, so welcome to the 14th video in Introduction to Quantum Field Theory. This is the first video in the second half of the lecture series. And in this video, we will cover a roadmap of free fields. So this book that we're following, No Nonsense Quantum Field Theory, will adopt natural units from this point onward. So natural units are here. So natural units, it's basically when you set c, the speed of light, equal to h bar equal to 1. You have all of these constants equal to 1. So we're going to write everything in natural units because it's easier to just write them in natural units than to try to figure out what they are in SI units, even though I think SI units are better. So the next 10 or so videos will focus on 4 extremely important ideas and 3 or specifically equations of motion. So the first equation of motion we'll focus on is the Klein-Gordon equation, which is for free scalar fields. Secondly, there's also the Dirac equation, and this is for free spinor fields. Then there is the Prolka equation, which is for massive, or it's for free massive gauge fields. And then the fourth, which is the Maxwell equation, which is the for a free massless gauge field. The solution, we'll see that the solution for all of these equations have a specific form, but before we talk about that, I'm just gonna move this up here so you can kind of get an idea of what the picture is. If you have a spin zero field, then it is described by a scalar, and that scalar field is described by, or the way the scalar field behaves is described by the Klein-Gordon equation. If you have a spin 1/2 field, then it is described by a spinor field, which is described by the Dirac equation. If you have a spin 1 field where mass is not equal to 0, then you have a massive gauge field, which is described by the Prokha equation. If you have a spin 1 field that is massless, you have a massless gauge field, and that is described by the Maxwell equation. Notice that in the limit that the Prokha equation, that the mass goes to 0, the Prokha equation becomes the Maxwell equation. You've never heard of the Prokha equation before? That's fine. It's a very simple. It's basically just a massive version of the Maxwell equation. A little neat trivia is that the Prokha is actually a Romanian last name, and it was discovered by a Romanian. That was actually something I learned when I was going to graduate school in Romania, because that was one of the things that my advisor tried to sell me on why I should go there. He's like, yeah, the Prokha equation. It's one of the 4 fundamental equations. Romania. Didn't end up being a good school, but whatever. So for the solutions, um, moving back to the form of the solutions, for the solutions to all of these equations of motion, we will make an ansatz, which is basically just an assumption or a guess. I don't know, it's just a guess or an assumption, but scientists like to use the word ansatz so they seem like they know what they're doing. So make an ansatz of the form that you have internal structure times space-time structure. Notice that we will assume that what this means is that we assume that the solutions have internal degrees of freedom and external degrees of freedom, and that they are uncoupled, namely that the internal structure changes separately from the spacetime structure. We'll see that the spacetime structure actually is always wave-like. So the major differences between these different types of fields is actually the internal structure, because this will be about the same. So the things that we'll see how the Dirac equation says that right and left vial, which also are called chiral spinners, oscillate into each other, into one another. Also see how the Proca equation says that massive gauge fields, so massive gauge fields have three uh, linearly independent polarizations. And likewise, we will see how the Maxwell equation says massless gauge fields have only two linearly independent polarizations. We've actually talked about this in previous videos. I think it was one in the videos where we were talking about the differences between scalar fields, spinor fields, and vector fields. In those videos, I talk about why you can't have why you can only have these types of polarizations. But we'll go over it again from a more field theoretic context.